Hello, everyone. Those of us believers in quantitative analysis as a factful evidence, I welcome you in today's lesson of showing a strong correlation between an independent variable as well as a very dependent variable, which, with degrees of confidence, we can infer that if we increase certain amount in independent variable, it will also increase or decrease certain amount in response variable. A change in dependent variable, a change in independent variable will cause a change in independent variable. We'll show association between dependent variable and independent variable. That is what we are going to show. In the last lesson, we showed the multiple regression analysis using the Statsmodels API function. Today, I am going to show you a complete manual calculation so that you understand, you control what you want to calculate. A complete manual calculation of the simple regression analysis. Okay, so for that, let's begin with import pandas as PD. I'm going to use pandas just to load and read the data, nothing else. Everything else will be done using NumPy. So import NumPy as NP. Okay, so these two models we'll use now, and later we'll verify the results with stat models. Okay, so let's go ahead and start this. Okay, now yes, gave a green check means those are imported. So now let's start defining the variables and all that. Okay, so our model is, you already know, model equals, okay, I'm just going to write you for this. Model equals y equals beta sub 0 plus beta sub 1 times x. Okay, so that is the model. We will compute beta sub 0 and beta sub 1 with the data. Okay, so begin with n equals, let me make it n equals 50. I want to give you adequate sample size, and x equals np dot random dot uniform. I want to generate data synthetically using the NumPy. So 10 to 100, you can think these as 10 million to 100 million in sales revenue. Okay, size equals n. Okay, size equals n, right? The sample size. Okay, that is x. X is independent variable called regressor, called predictor. Okay, y similarly equals np. Y equals, so what we're going to do to make it a encompassing the noise, the disturbances, we're going to use NumPy with this 5 plus 2.5 times x plus np dot random dot normal. Okay, this is just creating the data, 2.5 plus 2.5 times of x plus 5. That is what it says. Okay, so if it was, say, 10 million, it will be 2.5 is 25 million plus 5 is 30 million. That kind of idea. Okay, so here we're going to do 0. Normal distribution is mean 0 and standard deviation 1, right? So in R1 means 10 is the starting point in x, comma, size, same again, size equals n. Okay, that is our data. So what this does is, this is response variable with noise, with some disturbance term. Okay, let's print a few this. Print, I like to use f string, so f x range, it is a range, right? X range equals, I am going to put this x dot min. Okay, minimum value of x. We want to show you just the range. Okay, minimum value of x, that will be that 0.2f into degrees, 2 decimal places, comma, x dot max, okay, it's the same deal, 0.2f, okay, x dot max to f, And oh, I forgot to put the curlies because this is a variable to f. Okay, so that is the y range. Now let's load it. Okay, let me just write a comment here. Load / read data. Okay, with pandas. Okay, let's start. df equals pd.data frame. pd.data frame. Okay, pd.data frame. What we have? X equals x, the variable we defined. Y equals y. Okay, so that. And let's print data preview. Just the title I am going to show you. This is just to show you the title, data preview. Okay, and now let me print df.head. Okay, and as well as while we are at it, let's print the shape, which will show you number of columns and rows. Print f n data shape df.shape. Okay, so let's print this. On top of that, I must ensure that this number persists for that np.random.seed. You can put any number, 1, 2, 3. By doing that, no matter how many times I run the code, I will always get these numbers. They will not change. If I don't do that, every time you run the code, you will get new numbers. Okay. Now you see, this will persist. So do this quickly. Required calculations for simple regression. So whatever you will see below this will be all required for simple regression. Okay, so start with n equals len df. Now we did length of ds because we read the data with pandas and pandas data frame called df. So next, x bar equals np.mean. See, with NumPy, this is so elegant. np.mean. And y bar similarly, y bar equals np.mean y. Okay. Now we need sum of squares. Okay, sum of squares. All right, how do we get that? Make sure I try to make sure that you see all this. Sum of squares. Okay, so let's start with sxx. Squared sum of x, okay? Equals np dot sum x minus x bar, right? X minus x bar. Okay, and that to get squared we raise to the power of 2. That is sxx. Okay, x minus x bar squared. Similarly, syy equals np dot sum y minus y bar squared. Okay, now we need sxy, which is cross product. Sxy equals, okay, n p dot sum y minus y bar times x minus x bar. Okay, xy is y minus y bar times x minus x bar summed. That is what we get. That is what we get. Okay, let me just print this. Print f sample size. Print sample size, which I call it n here. Okay, equals n in curly. Okay, that is sample size. It will print sample size. Print mean of x. Mean of x is going to be x bar. Let's make it 4 decimal places. Okay, not too much, not too many. We don't want many decimal places. Okay, that's x bar, mean of x bar. Similarly, print mean of y bar. Let me just maybe put it down so that I don't have to type. Put it down. Oh, not yet. Print f mean of y bar. Same deal for f. Okay, so we printed mean of x and mean of y. All right, and let's print sum of squares. Print f. Want to show that in next line, so that's why I'm class n. Sum of squares. Okay, sum of squares. Let's go down. Print, we need to print those squares, right? F sxx equals sum xi x minus x bar squared. Okay, xi minus x bar squared. And that is that what we need to squared. We need to put in the variable sxx, find for f. Okay, all right, let's close the quotes. I forgot quotes in the beginning also here. Okay, that is sxx. Now we need to print the same syy sum of y minus y bar squared, and let's make this syy. Okay, that is that. And now we need the cross product, right? Print f cross product sxy equals sum y minus y bar and x minus x bar. X minus x bar. Okay, that is the formula. Let's get those variables in. SXY with 4 decimal places. Okay, so that is the cross product. So these are the numbers that we require. We are going to print. Let's show it. You see here, we got all the numbers that is required for calculating the sums. So now let's go towards fitting the model. Okay, fitting the model is going to be, I want to make sure you are seeing all this, fitting the model. So let me just write it, model fit statistics. Okay, let me print a title, print, let me just print 1 2 3 4 model fit statistics. One, two, three, four. Okay, just the title, nothing else. Okay, now here comes the real thing. Y prod. What is Y prod? Y predicted. Y pred. Y predicted. We need that, right? Predicted Y. Okay, how do we predict the Y? Equals B sub 0 plus B sub 1 times x. Okay, that will give us Y predict, which will require below for other things. Residuals. We need residuals, right, to calculate the errors. So what are the residuals? Y minus Y pred. See, right away. Y pred. Okay, sum of squares fit for. Let's go to calculate fit for model, to show how the model explains the variability. We calculate R square, right? So for that, let me write this one. Sum of squares fit for R squared. R squared. We need to get that. So how you do that? Let's clear some terminologies first. SSE equals NP dot sum. How do we get that? Some residuals. Let's do residuals because we already have residuals. NP dot sum residuals. Okay, raised to the power 2 gives us squared sum of errors. Okay, squared sum of residuals. Residuals is Y minus Y pred. Okay, now let's similarly get SST, which is sum of squared total. NP dot sum. So how do you get the total? Y minus Y bar squared. This is how you get Y minus Y bar squared. Let me put another bracket. Y minus Y bar squared. Okay, that is how you get Y minus Y bar squared is sum of total. Sum of square totals. squared sum of total. Okay. Now what else we need? Squared sum of regression, SSR, equals, what is that? SST minus SSE. SSE. So regression is explained part, which comes from subtracting the unexplained part. Okay, so now how do we get R square? R squared equals SSE, SSR over SST, SSR over SST. Okay, SST. So now let's get along with printing all this. Okay, print F sum of squared errors, which is SSE, is in the variable SSE 4 decimal spaces. Okay, that is sum of squared errors. Similarly, let's bring it down. Print total sum of squares. Print total sum of squared total. Okay. Now what is left? We have sum of squared total. We have this. Now R squared. Print F R squared. R squared. Okay, let's put in the variable R squared equals R squared. Okay, R squared. We would like that in 4 decimal spot. Okay, consistently 4 decimal spots. Okay, so this will show the cause of this error here is before calculating the sum of squares, we need to calculate these beta sub 0 and beta sub 1 times x, right? Which we haven't done. Let's insert one cell here and go ahead and do that. So here I will name it regression coefficients. COFCINTS. Okay. Regression coefficients. Okay. So start with the easy one, B1. Beta sub 1 is the easiest one, which is SXY divided by SXX. Okay. And beta sub 0 is equals y bar minus beta sub 1 b1 times x bar. Okay, x bar. All right, which we have x bar and y bar up there, right? So let's print them. Print f string. So beta sub 1, let's make it beta 1, beta 1, which is also called slope. Let's make that in a bracket, slope. Okay, that value is, we computed there. So for that, we have to just write B1 to the 4 decimal places. Okay, so that is beta sub 1. Let's go ahead and compute beta sub 0. Instead of beta 1, we will write beta 0. And this is called intercept. And here we're going to do it beta sub 0, not 1. Okay, so that will give us beta sub 1. So let's print those regressions, print those coefficients, print f in the next line, regression equation regression equation y equals beta sub 0 b sub 0 to the power of 4 to the 4 decimal 4f plus beta sub 1 b1 4 decimal, okay, times x times x. Okay, so that should be our regression. I have this squiggly because I need to put n here. Okay, so once we run this, we should be able to get that the regression equation with values of slope and intercept. Okay, sxy is not, so let me run all, because when such thing happen, it is due to this. See here, you can see beta sub 1 slope is 2.4632, beta sub 0 intercept is 8.0850. Regression equals this, y equals 8.0850 plus, making a fuss, SST equals NP dot sum y minus y bar raised to the power 2 is squared, right? 2. Okay, so that is SST. Similarly, we have that, and we should be able to see the R squared. You see here, model fit statistics, sum of squared errors, this, sum of square totals, this, and R squared is 0.9558. The model is pretty good. It's 95% explanatory power. Okay, so we have gotten up to there, right? Now, for the sake of you being able to analyze the parameters in the regression results run as a stat models, you should be able to calculate some of the standard error, beta, t values, and all that. I'm going to show you a few of them here. Okay, so for that, first we calculate, let me just write standard errors, and confidence intervals, which will be reflected by t values. Okay, so for first, MSE, mean square error. Okay, how do you get that? MSE is nothing but SSE divided by degrees of freedom, n minus 2 in the case of simple regression. Okay, all right, so that is one. Print MSE, print f dot mean squared error, mean squared error, MSE equals, let's get that variable MSE to the 4 decimal places. I'm putting 4 decimal places only everywhere. Okay, all right, so mean squared error. So if you want to get RMSE, which is nothing other than just the square root of MSE, so just put straight into the print statement, root mean root mean squared errors, RMSE is put in the variable np dot square root sqrt, np dot square root MSE, so also 4 decimal places, 4f. Okay, so this will give us MSE and RMSE. All right, so there is no point just calculating these we are calculating to show the standard errors. So let's do standard error SE of B1 equals NP dot square root SQRT, NP dot square root of MSE divided by SXX, XX. That gives us square root of standard error of beta 1. Okay, now let's go SE B2, B0, which will be NP dot SQRT. It's a little more involved. MSE times, create this 1 over n, okay, 1 over sample size, plus x bar squared. Okay, that will give us the standard error for intercept. Standard error for slope is given by SEB1. Okay, divide by SXX. divided by SXX. Okay. Now let's print those. Print F SE standard error of B1. Standard error B1. Okay, let's put in the variable standard error B1 SE B1 SE B1 again to the 4 decimal places for F. Okay, and let's print SE B0 for F. Okay, so that gives us standard errors. All right, the last part is let's calculate T statistics. Let me just say T statistics. So it will be T beta sub 1, T beta sub 0. Okay, so T B1 equals B1 divided by standard error beta 1 SE B1. Okay, TB1 equals SEB1. Similarly, TB2, TB0, I'm confusing here, B1, B2, it is B0 and B1. To B0 divided by SEB0. Okay, SEB0, you know why? Because I write, oh, SEB0. So let's print that. Print F. Okay, what do we want to print? Let me just get rid of this. Print F that T beta sub 1, okay, equals here T B1 B1 4 decimal places. Okay, let me close it. All right, so similarly print T B0 4 decimal places. Okay, so we print this. Now let me make sure you're seeing this, all that. So compute this. See here, SE beta sub 1 equals 0.743, SE beta sub 0 equals 4.0992. Similarly, T beta 1 33.14, beta 0 1.973. So now to check these numbers, one last thing we're going to do is to verify these numbers with stats model. For that, let me get that. Import statsmodels.api as SM. Okay, and now once I have done that, let's do x equals df x. Okay, let me see. Oh, df x should be larger x, and x y equals df y. Okay, and x equals sm dot add constant, add intercept, that will be x. Okay, similarly model equals sm dot ols y comma x, x is large, dot fit. Okay, that model. Now let's print it, and that's all we will do today. Print model dot summary. We get the summary method to display all that, and then we'll just verify. Okay, so let me run this, and I need to show you small x and y. Okay, so this was just a minor error. dfx x dfy. Okay, so let's see what it does now. Okay, you see here now, this is what I was saying, manual calculation to be verified by that. Okay, now look, let's verify this standard error beta 1, standard error beta 1. Where is that? Standard error beta 1. You see here, beta 1 is slope 0.76. So what I got? 0.0743. See, this is rounding, within the rounding, 0.076. And for intercept, 4.511. See, 4.091. So within the rounding. And similarly, look for t values. 33 t beta 1, which is the slope, is here. 32.214 here, 33.141. Beta sub 0, 1.97, 1.792. So you see, all within the rounding spaces. If I had done 6 decimal place or no decimal place, I would have gotten exactly those. So you can see that this verifies that our calculation have been correct. So R squared 9558. What we got? 956. You see, rounded. So coefficients. Now let's check the coefficient values. What was the coefficient value manually? What we got? Beta sub 0, beta sub 1, right? Sum of squared that. See, beta 1 was 2.4632, beta 0 was 8.05. So here 8.05. See, 2.46, all matches. So this is how I wanted to explain to you today that understanding the underlying factors in computing the regression analysis is very, very important to understand the principle behind how regression is carried out, the regressors, and how to interpret the coefficients with this lesson. I hope you are able to see. In practical life, usually it is just use the stat models like this I have done here. These are the practical way of doing. Okay. In the stat model, in Python, we have these stat models available. If you are using machine language, you can use linear regression library there, all kind of stuff, easy to do. But the intention today was to explain to you, to show you the underlying factors of arriving at a regression analysis, arriving at various computation measures to get the module, to fit the module, to get the determination of module, determination of fitness of module, and the standard errors and all that kind of stuff. Thank you for watching. I hope this was explained well. Please comment if some aspect is not clear. I look forward to reading your comment. Subscribe to my channel. This is very important aspect of learning statistics as well as Python and Pandas. Python and Pandas has become one of the, Pandas NumPy has become one of the most effective tools in data analysis and statistical analysis. Thank you for now. Bye-bye.